Continuing our last video, in this part, we will discuss projective coordinates and how they correlate to points on the projective plane. Now, in the Cartesian coordinate system, we have x and y axes, and a given point is defined by some value of x and some value of y in this fashion. But for the projective plane, we will be introducing a third variable, actually, the z variable. So we'll have x variable, y variable, and z variable, and these are usually separated not by commas, but with colons. And for projective coordinates, there's obviously a new way of describing the point, because we have three variables, and the x-coordinate of a projective coordinate, or of a point on the projective plane, is, think of it as the value x divided by the value z, and then a comma, y over z. So that is how we can look at projective coordinates in terms of x to z and y to z, and that tells us the location of a point on the projective plane. Now, the projective plane uses field theory, which is a little bit complicated to explain for the first time, but I will start by saying we know that x, y, and z are all in this field K. But we'll get back to that in a minute. In the meantime, just consider the following. We have x over z comma y over z, and that is just a ratio of our usual x variable to z, this third variable. So let's say that, for example, x equals 3, y equals 5, and z equals 7. That would mean that to describe this point on the projective plane, we could say 3 to 5 to 7, or in our head, we could think of it as 3/7 to 5/7. Basically, we can say that for any integer, in my book, it is described as for any lambda, it uses the Greek letter lambda, in the ring of integers, denoted with a z, well, actually, the z I got from a different source, but that turns out to be the official way of denoting the ring of integers, with a z rather than j, which is what they use in pre-calc, and that aggravates me slightly because z is the one that is truly used. Actually, it is usually written in Blackboard font. So z, the ring of integers, that is the official way of writing the set of integers. Anyway, getting back on topic, if we have any integer in the set of integers, it is important to note that for a projective coordinate, x to y to z denotes the same point as lambda x to lambda y to lambda z, as long as lambda does not equal 0. Now I'll let that sink in for a moment, but basically it means that because we're talking about ratios, if we have, say, 3/2 as our x value of our projective coordinate, meaning x over z equals 3/2, or really we can just deduce that x equals 3 and z equals 2. So from here we can say that if we multiply this ratio by some scale factor, so to speak, or some scalar constant, really it could be any k or any lambda, we will get some multiple of 3/2, right? We'll get 3/2, we could get 6 over 4, 9 over 6, something like that. Something where the numerator and denominator share some sort of factor. But if we factor that out, the most reduced fraction is just 3/2. So that is basically why it denotes the same point on the projective plane. Now this is a condensed example because it's only talking about an x value. It's only talking about what we call the projective line, actually, so it's condensed. But the same idea applies. Because we have some x value, some ratio here, and multiplying it by a constant, assuming that we carry through the constant to, lambda x to lambda y to lambda z, we get the same point on objective plane. So that's a very interesting property. We would ultimately be multiplying by k divided by k. That's what I was trying to show you. And of course k over k is 1, so it makes no difference. And that's what this really means. See, when I say k or lambda, they're basically the same thing. Just some constant sort of factor that we're carrying through and multiplying x by lambda, y by lambda, and z by lambda, such that it really creates, it results in the same point on the projective plane. That's what I was trying to say. Now, getting back to the idea that x, y, and z are all in some field k, we can deduce that if we have some projective coordinate, x to y to z, for all z, so for any value of this z value, of this denominator, not equal to 0, because we're not quite dividing by 0 yet, I'm just setting the stage, while the value of z is in R, the set of real numbers. Now, bear in mind, this could be R or C, it could also be Q, R being the set of real numbers, C being the set of complex numbers, Q is the set of rationals. These are all fields, by the way, all different kinds of fields in mathematics. And I would recommend very much that you look up field theory and read a lot about it. But long story short, it allows us to give some new value of x, I'll say x prime, actually, x prime to y prime to 1, as long as we use a field. So, in other words, no matter what we choose for our original x, y, and z values, as long as they're all part of the same field, whether it's the real numbers, complex numbers, rational numbers, there are other fields too, of course, but these are the main ones that I've mentioned over here. No matter what values we choose of x, y, and z, as long as they're not 0, or rather, as long as z does not equal 0, and as long as x and y don't both equal 0, one of them can be 0, but they can't both be 0, then there is some sort of lambda, some sort of constant scalar that we can multiply through to x, y, and z in order to ensure that z equals 1. And the reason we need a field for this is because a field is what allows us to use inverses, multiplicative inverses, actually, such that for every element of the field, there exists another element in that same field where when you multiply those two elements together, you get 1. So that is really the kind of the definition of a field, and what makes a field very useful to us. So if you think about it, that all of those cases where z does not equal 0 can just be condensed into a single case where x is part of some field, y is part of the same field, and z is equal to 1. So that's a whole sort of class of numbers. That's a whole... that constitutes its own case. But, I ask you, what would happen if we had something like this? x1 to y1 to 0. So now in this case, z equals 0, which means the denominator of both x and y, you can think of it as they're both divided by 0. That's a way of thinking of it in terms of our Cartesian plane, although it's not completely accurate. But it's still very interesting. And so that's what I'll proceed to tell you in the following. So let's study that second case where we have some x1 to some y1 to the value 0, assuming that third variable is equal to 0. In other words, we are dividing by 0. Now this is when things get very interesting in the projective plane. So our way of writing this, so to speak, in the Cartesian plane would be something like x1 over 0, comma, y1 over 0. So there is much analysis that we can do with functions in the projective plane, but first I would just like to introduce two important points at infinity. And these points have the values 0 to 1 to 0, and 1 to 0 to 0. Now these are the two relevant points we'll be studying.